least we know we're not going
Testing? Okay, hopefully people can hear me now.
all moderate.
Okay, sounds good.
So they're asking you to repeat.
Yeah.
Repeat or something.
Okay, hopefully the audio is back. I'll just repeat what I said. So, welcome back to day 6 of the Poly course. And today we're going to talk about the properties of the composition product, which was that other monoidal structure on Poly that I introduced way back on day 2. And we'll look at some interesting properties of it, but this will just sort of be a bit of a teaser until Thursday's class, where we'll really get into something really kind of wild about this particular monoidal structure. But before we get into any of that, we will cover some of the stuff that I missed at the end of class last time. And remember, if you'll recall, we were just going over some random other categorical properties of Poly, and we will go over them real quick right now. So one interesting thing about Poly is that there's a bunch of these adjunctions between Poly and set. And in fact, we have this quadruple adjoint between set and Poly, and I've depicted it here by telling you where each set in A goes in each of these functors, or sorry, each set A goes through each of these functors, and where each polynomial P goes through each of these functors. So so this is the functor that takes each P in Poly to P of 0. This is the functor that just gives us a copy of set in Poly by just thinking of all of the constant polynomials. This is our familiar on positions map that takes each polynomial and sends it to its set of positions. And this bottom map sends each set to itself times y, so the linear polynomial with that set as its coefficient. And so, in fact, these two sort of rightward functors are both fully faithful, and so we get these two copies of set in Poly, and we get these adjunctions with them. And you can, and what these adjunctions actually say are that all of these isomorphisms hold naturally, and we can see how some of these work. I definitely recommend you to try to actually work these out on your own just to get some practice with working with these polynomials. You could either try to do this by just expanding things out in terms of our formula for maps between two polynomials, or you could try to draw some of the pictures like the ones I drew last time to see sort of what is happening kind of intuitively. Yeah, Christian?
Sorry, that B.
Sorry, this should not be a B. I'm not sure where that came from. That should be a P. Thank you. Okay. And we actually have yet another copy of set in Poly, except it's a contravariant sort of inclusion from set op to Poly through the y to the a functor that takes each a to y to the a. And in fact, this is a right adjoint of our functor that we saw, that we introduced last time, which is this situations functor, or enclosures functor, which sends each P to the set of polymaps from P to Y. And in fact, we have this adjunction here, although you can see this one fairly easily by seeing that, so maps from P into Y to the A are just a bunch of maps from P to Y, one for each A, by the universal property of the product. And so we really just have one map for each A of a map from P to Y. Yeah. I think, so these are going to come up a bit. I think one takeaway from this is that since the onPositions functor, the functor that takes each polynomial to its positions, is both a left adjoint and a right adjoint, limits in Poly are going to also be limits on the positions, right? And colimits, the positions of a colimit in Poly are also going to be colimits of the positions, and so forth, right? Yeah, and in fact, speaking of that, here we have some other facts about Poly. And I won't go into these in too much detail. The details are in the book. Poly has epimono factorization. It turns out that monomorphisms in Poly are, in fact, just monomorphisms on the positions and epis on the directions in a very specific way. Now, epis in Poly are, you might expect them to be epis on the positions and the monomorphisms back on the directions, but it's actually a little more subtle than that. But again, the details are in the book, or if you're interested, you can ask me after class. There's also another factorization system in Poly, although these words might not mean anything until I introduce them here. So we'll use these once in a while. So a morphism in Poly, we call it vertical if it is an isomorphism on positions. And so I've just drawn a quick little map of polynomials here. The numbers tell you where each sort of direction goes backwards. But you don't really even have to worry about the numbers here, because you can see that every position just corresponds to another position. So this is an isomorphism of positions. So this is an example of a vertical map in Poly. Morphism in Poly is Cartesian if every on-directions function is an isomorphism. So in this case, the on-positions function could be anything, but the key is that each individual on-directions function back is going to be an isomorphism of directions. And so here we have a map that sends this position here to this position, and it sort of does the swap of directions backwards, but that's an isomorphism. Similarly, it sends all three of these positions to this one position, but you can see that these all are going to have to be sort of isomorphisms from one to one. And finally, we have this map from a sort of no direction position to another no direction position. That's another isomorphism. And it turns out that if you have, I should say that the place where this word comes from, why we call this a Cartesian map, is because if you'll recall, morphisms in Poly are natural transformations. And so this actually corresponds exactly to the idea of a Cartesian natural transformation, which is a specific type of natural transformation where every naturality square that you can draw out is a pullback square. And it turns out that these, if you work out sort of what that means, you'll see that this is exactly the same thing as saying that all of these on-directions functions are isomorphisms. And yeah, and it turns out that any morphism in Poly can be factored into a vertical map followed by a Cartesian map. And so you can sort of think about it's sort of like, because the vertical map is going to be an isomorphism on positions, so you kind of just like keep the positions the same, but only do stuff with the directions here. And then the Cartesian part is going to be isomorphisms on directions, so you kind of keep the directions the same and only do stuff on positions here. And then that gets you your factorization. And finally, Poly is complete and co-complete, so it has all small limits and colimits. In particular, limits in Poly, as I believe I alluded to, I think on day 2, are just going to be limits, a limit of the positions, the position of a limit is going to be a limit of the positions, whereas the directions are going to be given by a colimit of the directions. And the specific way that works out, I'll just give an example using a pullback. So for example, if we have a polynomial p and a polynomial q mapping into R, let's just call these phi and psi. This pullback, well, as I mentioned, since this p of 1 functor is both, or I guess specifically it is a right adjoint, so it's going to preserve our limits. So whatever this pullback is, its positions are going to be this the pullback of this sort of equivalent corresponding position square. Yeah, so if you think of these each as like p of 1, r of 1, and q of 1, that pullback in sets is going to give you the positions here. And this works in general for all limits, but then the next thing you need to do is figure out what each direction set of this polynomial is. And so the way we can do that is we pick some specific position up here in this pullback. So let's say we pick a position that's I comma j that maps to I down here, and it maps to j over here. So a position I of p and a position j of q. And these are going to need to map through phi sub 1 and psi sub 1 to the same position k of r. And so what you get, if you think about the what's happening on directions here, you get this square flipped around. So you start here at the directions of r at k, and you get a map according to phi. So phi sharp sub k over to p bracket I. You also get a map according to psi up to q bracket j. So this is psi sub j, psi sharp sub j. And if we build this push out, this is going to be exactly what we want for the directions at I comma j of our pullback. And in general, you can always for any position of the limit, map it to all of the positions of the individual polynomials in the diagram, flip all the arrows over to get a diagram of on directions functions, and take the colimit of that to get the directions of that polynomial. Any questions about any of those things? Okay, I think we're going to see a pullback later, which is why, hopefully, if we get to it, mention that, but yeah. Okay. So now let's get to the main course of today, which is our composition product. So we introduced this once before, but we can think of poly, the category poly, as a monoidal category whose, nope, that's the wrong one, whose tensor product is composition of polynomial functors. Except we're not going to use the circle symbol, which you might be familiar with for composition, for, I guess, a bunch of reasons. One is that it clashes with just the usual composition of morphisms. It's going to get confusing if we use this to also mean the composition sort of tensor product of two morphisms. And also, we want to emphasize that unlike all the other monoidal structures we've introduced, this is actually going to be asymmetric, right? P compose Q is not necessarily the same as Q compose P. So we're going to use this little triangle that is not a symmetric symbol to sort of distinguish between that. And there's also another, this triangle is going to evoke a particular sort of image with trees, as you'll see later when we introduce one of the other perspectives on composition. But first, very simply, we define the composite of two polynomials as literally the composite of them as functors, right? So P composed Q, if we apply it to some set A, is literally just P applied to Q applied to A. And so, for example, we can take y squared plus y plus 3, compose it with y cubed plus 1, and this literally just becomes, take this, plug it in wherever you see a y. So this really is just kind of middle school / high school algebra. And this gets you, what is it? So you get a y to the 6th. You get 2y cubed from here and an extra y cubed here. And you get 1, 2, 3, 4, 5. And that's polynomial composition. One thing to note right away is that, let's see, this is maybe too obvious to even say, but the positions of the composite are literally going to be P of Q of 1. So it's P applied to the positions of Q. OK, so that's what it looks like in terms of these functors. But let's actually, so we have the positions. What are, I guess one question is, what are the directions of this thing? Like, how do we think about these positions? And then how do we think about what directions this polynomial has as arenas? And yeah, so in order to figure that out, let's write out our polynomials in the way we usually write them. So we're going to write P composed with Q. Let's see. So P is a sum over the positions of P of something raised, of specifically y raised to the power of P bracket I. Right? And what we can plug in here is our formula for Q. OK. Now, we're going to write this out in a form that I guess might be a little easier to see, but it's certainly indicative of something. Let's see. So we're going to keep that. And so we can think of this as a product of this, of a P bracket I fold product of this thing inside. So we can write this out as a product over elements of P bracket I, except we're not actually going to use this D. And we can also write y to the Q bracket j as this product. And this is the kind of pattern, this sort of like alternating sum product pattern that you see in like game theory or something, and we'll kind of see how this kind of pattern really encapsulates exactly what we mean when we think about the composite of two arenas. Basically, right, we're picking a position of I, and for every, we're picking a position of I, and then, sorry, yes, thank you. Yeah, the way we want to read this is we're picking a position of P, namely I. And we're also picking, for each direction of P at I, a position of Q, namely J. And we're also picking for each, we're also kind of, we're picking for each direction of Q at J something. And so something keeps going there. Now, OK, but how do we actually find the positions and directions of this thing? Well, we're going to need to write this out as basically like a big sum and then a big product of y's, right? If we want to actually see what the positions and directions of this polynomial is. And so we need to flip these. There's a bunch of ways you can think about flipping these. One is if you're just thinking about these as polynomials, you're really just applying the distributive property. And so you have this big sum of a bunch of y to the q bracket j terms, and then you're raising that sum to p bracket I, you're going to get a bunch of terms, and each term is going to assign for each element of p bracket I some term in here. So it's going to be you're going to have a sort of function from p bracket I to q of 1. Another way to think about that is just looking at this directly, right? We are picking for each element of p bracket I an element of q of 1, and also for each element of q bracket j, blah, blah, blah. But another way you can think of that is that we just go ahead and pick a function from p bracket I to q of 1, right? We just pick that first. So we still have this. But then we pick a function, and I'm going to write this as j bar. Let's see, how do I want to write this? I'm going to write j with a bar on top just to remind you that this is a function and not just one element. So we pick a function from p bracket I to q of 1. Well, then what do we do? Well, we still need to keep doing this. So we still are going to need to pick for each element of p bracket I here, and for each element of q bracket j here, we're going to multiply a y. And so now we just have a double product here of that, and another product here. But here, instead of having a j here, we actually have this function. We've already picked out all our j's via this function here. So we just need to plug in this d into this function here. Yeah, and again, if you did this using the distributive property, you would have gotten exactly this. And so really, this is a thing whose positions are going to be positions of positions of p, which I'll use I always to denote, and a function assigning each direction of p at I a position of q. So these are our positions. Meanwhile, our directions, what is this? So to pick a direction, it's basically how many times we're multiplying by y here. And so it's going to be an element of p bracket I, as well as an element of q bracket j bar of d. So it's actually going to be two directions. It's going to be a direction at this top position here, and then another direction at whatever position we get when we feed this direction here. And so what kind of thing actually is this? We know what set, right, forms the positions. We know what set forms the directions, but how do we actually think of this? Well, let's draw these out as our Corolla forests. So let's see. OK, so if we take this example that we have over here, we have y squared plus y plus 3 composed with y cubed plus 1. And so as trees, as Corollas, this is going to be, so we have y squared plus y plus 3 composed with y cubed plus 1. OK. Take a sip of water. Yeah. So what are our positions of what we're going to get as a result? Well, we need to pick a position of p. Did you want to say something? Yeah.
Could we do the two polynomials in different colors?
Oh, that's a great idea. Yes. I don't know how well this is going to show up for the folks at home, but let's give it a shot here. That marker is not great. Go with this one, I think, is maybe a little better. just call this one Q. Okay, so we want, as our positions, a position of P. And then for each direction of P, a position of Q. So here's one way we can think about that. We can take one of these. Let's just take the very first position of P. We'll go in order. And for each one of its directions, we need a position of Q. Well, we could just draw these positions of Q at each of these directions. So again, we'll go in, I guess, lexicographical order. So I'm going to pick these positions to both be this one here. But let's actually draw out all of these. I don't think this will take too long. Let's see. So start with this. We can put this position here, and then this position with no directions here. Then we can do the same thing, but flipped around. Finally, the last one, whose bottom position is this one, is going to have two of these here. Now, let's take the next position of P. Well, it only has one direction, so we just pick one of these two positions to put here. And then we could also pick the other one. And then we have these three positions. Well, this position has no directions, so we pick for every direction a position here, but there's none of them, so we've already drawn it. And then we draw the second position, and then we also draw this third position. And those are our positions of P composed with Q. Now, what about the directions? Well, if we look over here, our directions are a position of P, a direction of P at the position we picked, and also a direction of Q at the position we picked for the direction we already picked. And that is just going to be a path of one of these trees of length 2 going up, starting from the bottom and going up. So it's going to be a path where you pick one red and one blue. And this blue has to start from this red. That's what this J bar of D being here means. And so you can think of these as these paths, or equivalently, you can think of these as the arrows that reach the very top, right? So for example, here we have 6 directions. So this is a y to the 6th term. This is a y to the 3 term. We have 3 directions here. Notice that we don't get to the top here, right? There's no directions of Q to pick if we come over here. So this actually contributes no directions. So if it doesn't reach the top, we have to ignore it there. This also has 3 directions. This has no directions because none of them reach the top. This is 3, and none of these have any directions. And so we see that we indeed have, as our composite, y to the 6th plus 3y cubed plus 1, 2, 3, 4, 5, just like we worked out here.
Is this a special reason for the triangle?
Yeah. Basically, if you look at it, right, this is kind of like, you can think of this as like a triangle, and then it's like going up. Yeah, I don't know, David, if you have any other way to explain it, right? Yeah.
P under Q.
Yeah.
Like we drew P lower than the Q with a triangle between them.
Yeah, right. So the reason why we draw this triangle facing this way is that we can think of like these corollas as being sort of like underneath these corollas, right, like as triangles, and so it sort of spreads out upward that way. And in fact, this works inductively, right? If we had a bunch of polynomials composed together, we could stack them to be even taller trees. And so if we had 3 polynomials composed together, we would sort of stack them all on top of each other and then look for these length 3 paths up the tree, and so on. And of course, appropriately, the unit being sort of being y, you can also, I know y we usually draw like this, but you can also sort of think of it as like a tree and like length 0 paths up this tree, right? So it's one, it's going to have one position and one length 0 path up the tree, so one direction. And so that's why y is basically the 0 composite, or the unit. Okay, yeah, so any questions about that picture? Okay, let's see what's next. Okay, now we told you this was a monoidal structure.
They want to know if it's associative. People want to know if it's associative.
Yes, I guess there's a couple ways you can see it's associative. Yeah, because composition of functors is associative, so that's one way you can see it's associative. Stacking sort of trees on top of each other, you can think of stacking sort of like if we had another R, a polynomial R, you could think of like stacking these on top of each other and then stacking positions of R on top of each of these, or you can stack these on top of each other and then stack them all on top of positions of P. That's going to give you the same thing, so it's still associative that way. Or even if you wrote it out like this, yeah. Great. Yeah, so we told you this was a monoidal structure, but we haven't told you what it does on morphisms yet. So let's take a look at what it could do. So let's have an example. Okay, I don't want to write this. Let's see. Okay. Yeah, let's see. So let's say we had a morphism that sent P to some other polynomial and also sent Q to some other polynomial. And we wanted to figure out the composite of those two morphisms and what it does on this giant polynomial. It's not that big, on this polynomial P composed with Q. I'm not going to draw out the whole morphism, and I'm not going to write this out formally, but hopefully you get sort of the idea of this. If we can start, let's say we want to figure out where this position gets sent to. Well, let me actually write. I'll at least write these out. So P, we have maybe some morphism from P to R, and then some morphism psi from Q to S. And so this morphism from P to R should give us a position for this bottom position of P to get sent to, right? Let's just say it gets sent to maybe a position that looks like this. And this is some position, let's call it a position, K of R. Now, we also need to stack on top of each of these directions a position of S to actually get a position of R composed with S. So how do we find each of these positions? Well, we take one of these, and then we go backwards along phi sharp to figure out where each of these directions takes us to. So let's say this, let's call these 1 and 2. Let's say this takes us to 2, this takes us to 2, and this takes us to 1. And we learned this from phi sharp. And what that tells us is that the positions of Q of interest here are for this one, for this one, still this one, and for this one, this position. And then we can send each of these positions through psi to get a position of S for each of these positions of Q. And so you can see, so let's say if this position got sent to maybe something that looks like this. Since this also gets sent to this direction, this position will get sent to that same position of S. And then maybe, let's see, this position gets sent to some other position that's going to look like that. Yeah, huh? Yeah, and it has to be sent to a position that without any directions. Yeah, and so that gives us the position of R composed with S that this position gets sent to under phi composed with psi. Now, of course, I also have to tell you where each direction gets sent back to, but that's not too bad because we knew that this position came from this position, and these are just this is just a part of the map of the map psi, and so this map psi gets us a direction, tells us where this direction gets sent back to amongst these directions, and so that actually tells us where this entire length to path gets sent back here, gets sent to here, and you can follow the same thing for each of these. And yeah, and that tells us how to compose, not how to compose morphisms, but how to apply the composition product on morphisms in Poly. Okay, and you can think of this also in terms of our decision-making language, right? Because we can think of this as sort of two protocols for passing on decisions. Here, if you'll recall, we can think of a morphism as saying P wants to make a decision. It sends its decision over to R, to one of R's positions. R picks one of the directions, picks one of the options, and sends that back to one of the options of P. And now we have another protocol here passing decisions between Q and S. And when we compose these together, it basically becomes a two-step process. It introduces some sort of like decision dependency, like decision kind of dependency to this. Because what's happening is P is sending one of its decisions over to R. And then R is, for each direction, it's sending, for each possible choice you can make, for each possible option, sending it back to one of P's options here. But P has already has decisions of Q ready at each of these options that could be sent back. So whatever P gets back from Q over here, they already have a decision of Q at the ready, which they send through this second protocol to a decision of S. And then an option of S is chosen, and it gets back to an option of Q. And so it's this two-step decision-making process. And you can see how composing more morphisms gives us sort of multi-step decision processes like this, and dependent decision processes. But really, it's combining all of these, and because you could have also thought of this as like someone sending a decision of P, but already telling you, okay, no matter what option I get back, I already know what my next position I'm going to send is. So I'm going to send all of that information forward, and then you just need to tell me what to do back. Okay. There is a particular way we like to write morphisms whenever these composites are involved, that I think David used briefly on day 3. But I'll mention it again because it's going to come in handy. Let's see, what do I want to talk about here? Okay. Yeah, so we're going to represent our polynomials. I think we saw how we can represent our polynomials as this sort of like domino kind of thing. So given a polynomial P, we're going to write a position down here and a direction up here. So an element I of P of 1, And then whatever direction, one rule for when we're writing these, whatever direction here automatically has to actually be a direction at this position. So it's a D in P bracket I. And so this by itself isn't all that useful until we think of it as a morphism. So another way of thinking of a polynomial morphism, it's actually really just a rephrasing of our decision-making interpretation, is as a kind of spreadsheet. You can think of these as cells of a spreadsheet, where this is P, this is Q, and so for each position of P that we write here, I'm not going to actually write I in P of 1. Whatever I write down here is going to be assumed to be a position of P. It's going to get sent to a position of Q here via some phi sub 1. And whatever direction gets picked up here gets sent via phi sub I sharp to a direction of I, at I up here of P. And the way we want to interpret this is thinking of this as like a spreadsheet where there are entries that you can fill in, and also entries that are automatically computed, right? Like that's the kind of thing you'll see on, like, I don't know, Google Sheets or something. And so these circles, we write these circles to represent, or I think in the book we actually shade these, we write these circles to represent things that you can fill in, right? So if, and we think of the entire morphism as this gadget that spits things out when we fill things in, right? So we can fill in something here, and it's going to spit out something here automatically. And we can also fill in something here, and it's going to spit something out automatically here. And the arrows kind of show sort of how the information travels, although one thing to be aware of is that like this, right, like this arrow isn't just dependent on this circle here, it's actually dependent on all of the things we've already filled in. So it's also dependent on this circle here. Yeah. And this actually makes it really easy to talk about a certain kind of map into one of our composites. So if we, instead of this, we had a map P, what am I saying? A map psi from P to Q composed with R, we could write this as like so. See, this is P, this is Q, this is R. Again, we can give a position of P, right? That's something we contribute. And this spreadsheet is going to automatically tell us a position of Q composed with R, just like it did up here. But a position of Q composed with R, let me draw this a little better here. A position of Q composed with R is actually comes in two parts. This is like Q composed with R here. It's going to give us a position of Q, but actually it's also going to give us a position of R, sorry, yeah, a position of R for every direction of Q at J. Oh yeah, sure, I'll just put an I here. And so whatever we give here, it needs to give us back, the spreadsheet needs to give us back something here. So if we put a direction there, the spreadsheet needs to give us back, let's give this back 0. The other way. Like this way? Yeah, sure. Yeah. OK. And then finally, just like here, if we give a direction up here, so really it's the direction given by both of these things up here, it's going to send this back to a direction over here. And we can see that we can map into multi sort of polynomial composites like this, and you get sort of these pictures where you get a bunch of like chains up here all the way going back here, and you can think of these maps like this. And in fact, I think on Thursday David will draw some other maps like this, and we can kind of see certain equations out of these. But one particular map I guess I will draw with this right now is I want to point out that there's always this canonical map from P tensor Q, the polynomial whose positions are pairs of positions of P and Q, and directions are pairs of directions of P and Q at those positions into P tensor Q. Now, the way I'm going to draw P tensor Q, I'm just actually going to draw, this is really just two polynomials like glued together, right? It's really just like P here. Actually, I'll draw them. Write that down here. P here and Q here, where to fill in a position of this, we fill in a position of P and a position of Q. And now, in order to give a map, I need to tell you what this is for whatever you plug in here. I need to tell you what, draw it on the other side again. I need to tell you what goes here for everything you can put in here. And I also need to tell you what goes here for everything you can put in here, for every direction you can put in there. And this is P and this is Q. OK, and what I am going to say, well, I need to put a position of P here, given what you put here. So what can I put here? I, right, that's the only position of P available here. OK, and let's say you give me a direction D there, and now I need to give you a position of Q for whatever you put in here. So what can we put here? Just J, yeah. It actually doesn't actually matter which direction you put in here. We're always going to put in J. And now you're going to put some direction of Q at J here, and now I need to give you a direction of P at I and a direction of Q at J, and I just fill in what you've already filled in there for me. And this is this map. So you can always get this map between any polynomials P and Q. And you can also kind of think about what this does as trees. What this is really doing is it's taking, right, because we can think of positions of P tensor Q as a tree in, for example, up there, a tree in P, sorry, a Corolla of P, sorry, position of P, and another a Corolla of Q. I'm just going to pick these two. But the positions are going to, sorry, the directions are going to be pairs of directions here. So while I can think of these pairs here, I can also just stack these on top of each other and put one copy of this for each direction up here. But that's just a position of P composed with Q. It's just one of, it's just a very specific position here where everything on top here comes from the same position of Q. And so really we're just sending this to this here. And you can see that this map is actually going to be Cartesian, right? Because it's just going to send all of these directions to themselves here, and there's nothing extra happening there. Yeah. OK. Let's see. I have 5 minutes left. And so I don't think I can get to both of these, but I think I'll cover one of them. I guess I'll just briefly mention, again, you can check this in the book, that we have these specific ways where the composition product interacts with the tensor product in what's called a duoidal structure. And this also applies to composition product with times and the composition product with sum, but maybe in different directions. But one thing I want to point out is how our composition product interacts with limits. Yeah, with limits. So one thing to note right away is this sort of fact. Again, this is really just a high school algebra fact that if we have two polynomials, P plus Q, and we compose it with another polynomial r, it's really just the same thing as p composed with r plus q composed with r, right? That's just how how polynomial functions work, huh? Do you want these? Yeah. Okay. Similarly, if we do p times q composed with r, it's really the same thing as p composed with r times q composed with r. Right, so on the left side here, right, we composition is going to preserve these coproducts and products. In fact, composition is going to preserve all limits and colimits, or just okay? I think all limits. Yeah, don't quote me on colimits because that's. But yeah, we'll focus on limits for now. On the other hand, it's pretty clear that this is not always going to work out. If we do a product on the right side, because, right, like for example, if we just let p be like y plus 1, right, and then maybe let q, I don't know, we can let q be 2 and r be 3. Well, y plus 1 applied to 2 times 3, that's going to be 7 on this side, whereas this is going to give you, what, like 3 and 4, and 3 times 4 is not 7. Or even, we could even just let, if we, let's see. Yeah, so, okay, so basically the point is that that composition does not preserve limits on the right. Another way to see this is if we even just plug in the terminal object 1, we don't have that this is the case, right? That composing with the terminal object is not going to give you
You do have that on the other side?
the terminal 1. Huh?
You do have that on the other side?
Yeah, but we do have it on the other side, yeah. Because 1, a constant polynomial composed with anything gives you that same constant polynomial. Right, but we do actually have something that does work, which is that composition is actually going to preserve connected limits on the right. And by a connected limit, we mean a limit where the underlying category, the underlying shape of the limit, is a connected category. And the empty category here doesn't count. So if we take, yeah, if we, for example, if we have a pullback square, let's see. Actually, I'm just going to use, yeah, so even though we can't compose, even though we can't preserve products, we can think of any product as a kind of a trivial pullback square. Right, this is q times r here. And if we compose p with this, what we get is a square that looks like this. And let's see. So, yeah, so what is this telling us? Well, if we have a position, okay, I think we're almost out of, I guess we are out of time. But yeah, it turns out that this is also going to be a pullback square. You can check this on positions. Again, on positions, a pullback is just a pullback in sets. And then if you go into directions, you'll notice that this is really just p of 1. So it's a constant polynomial without any directions. So this pullback square, you flip it, it's a push-out square, but it's really just a coproduct. And so it's just going to be the directions of these are just going to be the sum of the directions of each of these. And you can check that this is actually, in fact, what happens when you do p composed with qr. Okay. Sorry for the rushed ending there, but yeah, any questions? If not, thank you all. Josh, do you have something?
Do we have